Here is what we are going to start with. You do not need your notes for this yet. The first question is not on your notes. We have a building. And on this building, we're dropping. It says a rock. I imagined a golf ball for some reason. But whatever. A hard object toward the sidewalk where there's magically no people because we wouldn't want to hurt anybody, right? And it's giving you how far it's fell, or how far it's fallen, after a certain number of seconds. What I want you and your partner to do is come up with how far it will have fallen after 6 seconds. All right, so I had a great time going around talking to everybody. And I had somebody calculate a distance. RJ did for sure. I don't know if anybody else did. But here's what I heard most people saying. From 4 to 5 seconds, it went up 240 feet, right? And what are you guys noticing about the gap each section? It's getting bigger because gravity, it's accelerating with gravity, right? So that means this gap, would it be more or less than 240 feet? More than 240 feet. And there's only 100 feet left. So it would hit the ground, something like that. Yeah, or 500 feet, right? It will not be falling for 6 seconds. So you guys seeing that? Yeah. Now, we're going to talk about what Jada noticed. And maybe you noticed it in the warm-up. For 1 second, she noticed 16 times 1 was the 16. 16 times 4 was the 64. 16 times 9 was the 144. 16 times 16, 256. And 16 times 25 was the 400. What seems to be a factor there over and over? 16 is certainly there over and over. So there's something else going on. She noticed that all of those things were perfect squares. So let's check this out. She noticed that all these were 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Right here. So what I want you to do is use Jada's observation to predict how far a rock would fall off an infinitely tall, a building that's tall enough. You're going to predict how far that rock would fall if it fell for 7 seconds. And then you're going to write a function for our context of this falling rock. With your partner, let's go. Okay, so who can give me a 7-second prediction using Jada's method? What'd you get, Grant?
I got 784.
And how'd you get it?
I squared 7 and multiplied it by 16.
So you did 16 times 7 squared. So that's what Jada has been doing, right? 16 times 2 squared, 16 times 3 squared, and so on. So who can help me out with an equation that will work for any number of seconds then? Willa?
X to the power of 2 times 16 equals y. No, it was t and d.
I did a y there. Yeah, but you got the right idea. The distance is equal to 16 times the time squared. This is the basic gravity formula that we'll see. And you'll see variations because there's things like we were saying, wind resistant, other factors, but this is kind of like the base, all right? With that, everybody's good? Everybody's got this down in your notes? We're going to see this again, y'all. We're going to see this again. And there's nothing else here. Later, we'll see this thing called acceleration. Why isn't there any acceleration happening here? What are we doing? What are they doing with the rock? Dropping it, which would be different than throwing it. Yeah, so look forward to in the future seeing more stuff happen to this function. We've got a quick video to watch. I'm interested to see how this translates to the video for the notes. Hope you guys like Galileo. Oh, it's playing on my laptop. Guys, we gotta start this over.
Balls, feathers, eggs, apples to the top of the Tower of Pisa.
I forgot that it was on my computer.
Faster, the big heavy ball or the small lighter ball? In my day, everyone believed that heavy things fell faster, and I wanted to prove them wrong.
You guys know, like on the moon, because there's like no atmosphere, a feather and a bowling ball that hit the ground at the same time.
No, because the feather has like the weird.
Not on the moon though.
Not on the moon.
Okay. Also, what weighs more, a pound of bricks or a pound of feathers? What do cows drink?
The first way more.
Okay. I was trying to hit you with some
I
trick ones.
carried various rocks, cannonballs, feathers, eggs, apples to the top of the Tower of Pisa.
You're just yeeting stuff
And then
off
I
the
dropped
tower.
them off the top.
Just
My
missed.
experiment prove I'm a very clever guy. The big heavy cannonball and the teensy little one both hit the ground at the same time. Heavy thing, lighter thing. You drop, they fall at the same speed. Which do you think was...
All right, so here's what you're going to do with gravity. Here's what you're going to do with this. So we've got this basic gravity function that we just discovered, and it is given right here. I just write it like this. I don't write the times thing in there, right? And we know it's what type of function? How do we know it's quadratic? There's a square. Instead of an image now, it's in the function, right? There's a square in the function, t squared. You're going to say how far it drops after 0.5 seconds. You're going to fill out the tables and explain the similarities and differences between the tables. Let's take a look. So Elena's table is the table of our original building, right? Yep. And what Elena's measuring is how far the rock has dropped, or the falling object. So after 64, 3 squared times 16 is what?
44.
And then 4 squared times 16?
256.
And we've got that 16t squared popping off again, right? Everybody good? So that's how far it's traveled. Who can tell me what's different about Diego's table?
It's how much is
Emmett,
left.
how much is left? So I'm going to take away the 16t squared from the height of the building, which is 576. So to get the 3, I'm only going to write this once. I would do 576 minus 16 times 3 squared. I'm going to take away how far it has fallen from where it started. So how much is left at 3? 432 is left?
Yeah, and then 320.
And then 320. And you can get those by substituting in time here, right? The building height minus how far it has gone. So the building height is 576, and we're subtracting our 16t squared, which is how far it went. So when I go look here, how are they alike?
They're both...
Finn. Not exponential.
Quadratic.
They're both quadratic, yes. Soldier Boy's favorite. What else is the same about them? Yeah, Micah?
They both use the equation of gravity.
So 16t squared is involved. I was looking for one of those like layup ones here. Emmett, you got it?
They both are talking about the same building in context.
Okay, same context. I was looking for someone to say the independent variable is time in both. And the dependent variable is a distance in both, right? So what's different? Okay, so we got an increase versus a decrease. But why is Diego's decreasing?
Because it's counting down the time, feet left.
This is the amount left, and this is the amount traveled. Or amount fallen, right? Same context, different variable tells us different things. You might want to know, like, hey, when's this thing going to hit the ground? And that's actually what I'm wondering. This isn't even in the lesson plan. I want to know when that thing's hitting the ground. Figure it out. So you guys probably guessing and checking. I heard 6 being thrown out there. There's a way to math this thing. So if I'm trying to get 576 to be 0, how much does this chunk need to equal? I need to take away 576, right? So here's what I'm going to choose to do. I need the distance traveled to be 576. Are you guys seeing my equation is like what I'm looking for? I want the distance traveled to be 576. So I'm going to divide both sides by 16. And guess what I get?
6.
I get 36.
Well, yeah.
How do I undo square?
Look at 6.
6.